All right, one method, one method for solving simultaneous linear equations. I just call this systems of equations because it's a lot easier to say than systems of simultaneous linear equations. So a system of equations is just where we have lots of equations that are all equivalent. Now on a graph this is extremely special because it's extremely easy to figure out what the answer is as long as you remember the stuff that you from last unit, which of course after the weekend no one will remember. So it won't matter because we're going to keep doing that stuff at least for this lesson. Okay? So consider the simultaneous linear equation shown below and answer the following questions. What problems might you encounter as you graph these two equations? So looking at these two equations, would you encounter any problems?
The first one is written in slope-intercept form.
Yeah, very good. That first one is not in slope-intercept form, but again, we've already learned how to change those into slope-intercept form, so hopefully it's not too bad. The second one is in slope-intercept form, so hopefully that would be okay to graph. So this is, again, should be mostly review. Now when graphing these two equations, again, we should be able to see the answer, which we would then write down. As we have seen, it is possible to rearrange an equation that it is not in slope-intercept form using the same rules we use to solve equations. We can rearrange this equation to put it in slope-intercept form. Remember, slope-intercept form is y equals mx plus b. So our goal here will be to isolate y on the left side of the equation, then arrange the right side so that our slope comes first, followed by the y-intercept, y equals mx plus b. There we go. All right, so up in here, we can see that to start off, they subtracted 2x from both sides. So something like these. And then all they did is they switched the positions of these two terms, 4 and negative 2x, which gave us y equals negative 2x plus 4. Now, of course, we got our y-intercept at 0, 4. And then we got a sloppage of negative 2, or negative 2 over 1, which would allow us to graph this line. Well, let's look at another example. They said this one's a little bit more challenging, but whatever. But with my help, apparently, we can write the steps as we complete, as we go. All right, so the first thing right here, we can see that they had subtracted 4x from both sides, which give us this next equation. And then after at these, they divide everywhere by negative 8, which gave us the next equation. And then, of course, we just switch the negative 2 and the 1/2 x to get our answer, okay? This process works pretty much all the time. In fact, on the previous example, instead of dividing by the coefficient of y, which was 1, we didn't need to because that's the identity property. So on that previous example, this purple step right here was skipped it. All right, then let's change all of these into slope-intercept form. Bam, here we go. What I will do first is subtract 5x from both sides, because we want a y equals some good stuff. Now this becomes a 0, and I got a y equals 9 minus 5x. So I have two terms, 9 and negative 5x. So if I change these, negative 5x, and then make that was a positive 9, equals a y, slope-intercept form. Now again, it's important to recognize which of these is our y-intercept. We could graph that and then use the sloppage to figure out where the other points on the line is, or B. Alright, here's B. So again, if I can get this 2y all by itself, then we'll be in good shape. So let's get rid of this 4x by subtracting 4x. And again, that will cause that to become a 0. And now I've got my 2y equals negative 12 minus 4x. Now if you wanted to switch those right now, you could. But based on what we did the last time, we had a coefficient of y. we had divided by 2 right now, and again, it wouldn't matter. So dividing by 2, we get a y equals negative 6 minus 2x. And then we just need to switch these. So I'm going to take that negative 2x and put it in front. And then I got that negative 6 as well. This is equal to y. Bam. Alright, see, it has a little bit different format. This isn't technically standard form, even though it kind of is, because we got the 4y first. So again, we need to get rid of that minus x by adding an x to both sides. So this becomes a 0. We got 4y equals 16 plus x. Now I can make that a 1x. It's not going to matter. The only reason I would do that, well actually let's do this one a little bit different, okay? Then we'll talk about why that's important. So I can switch these now. I got 1x and then a positive 16 radical. This equals 4y. So to solve this, I would divide everything by 4, and that's where the 1 comes in. Because now we can see that y, or 1y, equals a 1/4 of an x plus 16 divided by 4 is 4. So we can see the y-intercept is 0, 4, and the sloppage is up 1 to the right 4. Okay. So what do you guys think we would do first radical? Yeah? There we go. Let's subtract 4x. But again, if I do it to one side in an equation, to maintain balance, we got to do it to both sides. So that's a 0. I'm left with negative 2y equals negative 24 minus 4x. Now what should we do? Yeah?
Divide everything by negative 2.
That sounds good. Divide everywhere by negative 2. So this becomes a 1y. That's good. That's what we want. Negative 24 divided by negative 2 is 12. And negative 4x divided by negative 2 is a positive 2x. The final thing is just to switch these. So we got y equals positive 2x, and then we got a positive 12. There it is. This one's a little tricky because it's not starting anywhere near standard form. But what's good is that we can see the coefficient of that y is negative 1. We don't want negative y, we want positive y, so to do that, we'll just divide everywhere by negative 1. Really, all that's going to do is allow us to take the opposite of each of these. So for example, the opposite of negative y is positive y, that's good. The opposite of x is negative x, and the opposite of minus 2 is plus 2. There it is, slope-intercept form. So this one does go back into standard form. Problem with this is that it's okay to have a fraction as a coefficient of x. So let's look at this one. Let's add 2x to both sides. So that zeroes out, and we're left with 5 of y equals 3 plus 2x.
Divided by 5.
So sure, let's divide by 5 everywhere. And again, that becomes a 1y, that's good. So then we got y equals 3/5 plus 2/5 of an x. And then we'll just switch those. Y equals positive 2/5 x, and then a positive 3/5. That'll do it. Consider these two linear equations. We're going to graph both of these on this graph here. All right, so 2x plus a y equals 4. Yeah, this one actually may take a little work. So let's change this into slope-intercept form. We got 2x plus y equals 4. I'll subtract 2x from both sides. So, yeah, we can change this right now to be negative 2x plus 4. And this would equal y. So, I did skip a step there, but some of you guys get that and don't need that step anyways. So we already did this one anyways. So we got y equals negative 2x plus 4. That gives us a y-intercept at 0, 4. So that would be this point right here. And then my sloppage is down 2 to the right 1. So down 2 to the right 1. And we'll continue this pattern on the graph. And I can go in the other direction if I wanted to use the stair-step method. But whatever. And now I got my line. So again, hopefully this isn't anything new yet. So we'll do the next one in Poiple. Now again, this is 4x minus 2, which means our y-intercept would be at 0, negative 2, or that the y value is negative 2 on the y-axis. So that's our first point. Then again, we'll use the sloppage on this one. I'm going to make it up 4 to the right 1, which would give us this point, this one, and this one. And we can go the other direction, 1, 2, 3, 4, and this point as well. So connecting these with a line is this. So the next question on the worksheet, then that's what it is this point right here is where these two lines intersect. That is the solution to this system. The answer is 1, 2.
Is there a way to find it?
So we found the point of intersection, and that was 1, 2. But then B, it says to verify that the point of intersection you found satisfies both equations. What this means is that we're going to take this 1, 2 value, and we're going to go back to the two original equations. So the red one was 2x plus a y equals 4. And then the purple one, y equals 4x minus 2. And we're just going to make sure that it gives us a true statement. If one of these is false, it means that the point actually is not on one of the lines. And it would, well, that's not where they would intersect, okay? So we'd have to go back and check and see where perhaps we may have made a mistake. So again, I'll replace the x and the y values in both equations with the values that we found. So, up in count, x is 1, so I'll replace x with 1, and I'll replace this x with 1, and the y is 2, so I'm replacing the y with 2. Now again, we're just looking for true statements here, so 2 times 1 is 2. Plus 2, does this equal 4? Sure it does. So this one is true and it checks off. But what about the next one? 2 equals 4 times 1 is 4 minus 2. 2 equals 4 minus 2 is 2. That's true as well.
Sounds like real math.
Well, yeah.
I know it all.
So since both of these are true, we know that it is the answer to both equations. So yeah, I mean, we haven't done a lot of this kind of stuff in a while, but solving equations like this, it's really evaluating the expressions. Hopefully that's not too new for you guys. But checking is one of those things that not a lot of people do, but it's a good way to guarantee that your answer is correct. It's very nice. So that was part B. So the solution to a pair of simultaneous linear equations is all pairs, if any, of numbers x, y that are solutions of both equations, that is x, y. It satisfies both equations. When solved graphically, it's the point of intersection, if there is one. So let's look at this 6. This would be after we had graphed. We found the point of intersection to be 3, 8, and then we just want to check our answer to make sure that it's correct. So let's look at that top equation first. If either one of these is false, then it is not a solution. So I'm going to replace my x and my y with the x value is 3 and the y value is 8. And we just want to make sure that's true. 2 times 3 is 6 plus 8. Does this equal 14? I'm going to put it in the calculator. Bam, there it goes. 14 does equal 14. That's true. So I do need to check this second one. X plus y equals 11. Again, replace x and y with 3 and 8. 3 plus 8 is 11. That also is true. So is this a solution? It is a solution. But, you know, it was fun all the while. All right, here we go.
Yeah.
So on this one, 7, right? We'll do this in different colors. X is going to be red, and the y value, -5, will be purple. So I'm going to replace this y with -5, right? And I'm going to replace the x with 0. Well, what's 2 times 0 minus 5? That one's -5. This becomes -5 equals, well, 0 minus 5 is -5, so that's true. That's good. What about the next equation? So again, x we'll replace with 0, and y with -5. So solving this, 4 times 0 is 0, 5 times -5 is -25. Does this equal 25? 0 minus 25 is -25, which I can do in a calculator, if I need it. Now I've got -25 equals +25. Is that true? Nope. Owing someone $25 is not the same as having $25. Okay? So this one is false, therefore this one is not a solution. Bam. All right, let's look at these two equations. Y equals -2x and y equals -1/2 x minus 3. Make sure both equations are written in slope-intercept form, then graph both equations. Verify that the solution satisfies both equations. Here we go. All right, so here's our two equations. And the red one, this one is in slope-intercept form. The problem is it doesn't show the plus b stuff, which means that it's really adding what?
0.
0. Very good. So the red equation will have a y-intercept at 0, 0, which is the origin right here. And then my sloppage is up 1, down 2. It's -2/1. So down 2 to the right 1, and this pattern just continues. And it continues in the other direction as well, which again is just showing us where the points are on the graph. So these are all points, and we just need to connect them using a line. That'll do it. Now if we want to just clean this up, not like that. If we want to clean this up, we can. It will let us, the jerk. Alright, let's try the purple one then. So again, we got our y-intercept at 0, -3, with a sloppage of -1/2. So 0, -3 right here. Sloppage, I'm going to make that actually a down 1 to the right 2. So down 1 to the right 2, down 1 to the right 2, and so forth, gives us these points. Now technically we would say that there's no reason to continue the graph, but I like it to be really pretty. So there's our points on this side as well. And we can graph this line. Bam, nailed it. So where do these two lines intersect? I got the point right here, which just happens to be 2, -4.
Why is that so special? Oh, friend.
So,
No, but you said it just
Yeah.
happens to be 2,
Yeah.
-4.
well, that's really special because lines like this, it's unfortunate because you guys like to read, it seems like. So it's kind of like two people, they like each other, but they meet once and then they drift apart forever and ever, right?
So one next statement.
Is if we check this stuff right here in both equations, we get a true statement, right? So our answer right now is 2, -4.
Whoa, that's a big 2, -4.
Well, yeah, I needed a little bit more space there. All right, so in these two equations, we got a y equals -2x. Well, once again, I'll replace the y and the x values. X is 2, and y is negative 4. Negative 2 times 2 is negative 4, which does equal negative 4. That's true. And then the other equation, y equals negative 1/2 x minus 3, and we'll replace the y value in x again with their respective values, which was negative 4 and 2. So negative 1/2 times 2 is negative 1 minus 3. This should equal negative 4, and it does. That is also true. So since both of these are true, we know we did that correct. And our answer is good. And we can circle that with confidence on a test. All right, number 9er, same idea up in here is, well, let's look at this negative 2x plus a y equals 1, because that's not in slope-intercept form. So if I add 2x to both sides, then I get y equals 2x plus a 1. Well, this gives us a y-intercept at 0, 1, which would be right here. And then my sloppage. Again, I'll make that 2 over 1, so I go up 2 to the right 1, up 2 to the right 1, up 2 to the right 1, and so forth. And I can continue this pattern to the left. Whoops, that's not where that goes. There we go. And then I'll make my line. Bam. Very nice. Now the next one, y equals 2x plus 4. So we got a y-intercept at 0, 4, right here, and a sloppage of 2 over 1. Now before we graph this, let's take a look at those two sloppages. What do you notice? Yeah?
They're ugly.
They are both positive. There's something else there, though. Yeah.
They're the same.
They are the same.
Wait, they're terrible.
That is excellent. These will end up being parallel. So where will these two meet?
Never.
See, and this is the tragedy of parallel lines.
Is they will never be together.
Parallel lines, as it turns out, they have a lot in common. See those sloppages? But again, like a romance novel, they have so much in common, but they will never meet. It's enough to make one cry. So really this comes down to what the actual answer is. Now we've already identified that these are parallel, so when will they meet? Never. So we would just say that this one has no solutions.
And then, can we circle that with confidence, Mr. Sal?
As long as you know that you've graphed them correctly, then yes. All right, let's take a look at this one. So based on what I'm hearing, you guys may hate this right now because it may not make sense, but you guys should like this a lot. Okay, here's why. Let's look at, what's that?
You only draw one line. Victory is ours.
Yes, that's right. So this is equal to 3, so if I subtract x from both sides,
Would that be considered one solution?
you'll find out. So this becomes a y equals negative x plus 3, which gives us a y-intercept at 0, 3, and a sloppage of negative 1. We'll just make it negative 1 over 1. So graphing that point, 3, 0, 3 is right here, and then down 1 to the right 1, continuous. All right, so there's our points. Let's just go ahead and graph those now. There we go. Now this other equation, 3x plus a 3y equals a 9er. And let's subtract 3x from both sides. And I got 3y equals negative 3x plus a 9er. So dividing everywhere by 3, I get y equals negative 3x, well no, negative 1x plus 3. So this gives us a y-intercept at 0, 3 and a sloppage at negative 1 over 1. So if I graph those points, as it turns out, I get the same points that I had on the red line, and therefore
They're meant for each other.
these ones are just brought together.
They're best friends
Now you guys said, well, this one's kind of rough, but the nice thing about this is that how many lines do we have to graph? One. So these two have a lot in common, and they're always together.
Probably MAGA parties.
Which again would be a nice romance novel there for you guys. You can include all three of these, right? Sometimes they meet and they drift apart forever. Sometimes they have a lot in common but never meet. And these two have everything in common.
This is gonna be the irony of number 2 is
But then
that
it can be like a
we're so
twisted universe where it's like the same person,
We're
okay?
like,
So this one, how many solutions?
My arm is 2 feet.
Where do these two intersect?
2 miles because then that would be good.
Where do these two intersect?
Everywhere.
Everywhere. So we just say that this one has infinite solutions. That's very good. So we did these 3 examples. Notice right here on number 8, we had different sloppages, okay? So that's something we can remember. If we have different sloppages, automatic,
Number 8.
one solution, okay? Well, mine says number 8. This next one, for me, is number 9. I think it's 2 for you guys, right? This one has the same sloppage, but different y-intercepts, which causes them to be parallel, okay?
Parallel.
Now on this third one, we have the same sloppage and the same y-intercept, which cause these to have the same exact equation, and so we have infinite solutions. These,
Talking about the parallel ones, I've always wondered.
yeah,
Do you have like
yeah.
a double somewhere in the universe that's maybe like 100 miles from you, and it's gonna be like impossible to ever see them because you always walk in the exact same like pattern, so you're always 100 miles.
Yes. Just like these two, in this 2-dimensional stuff they meet, but if we made it 3-dimensional, one could be out here, one could be back here, and they would just never actually touch. But in this 2-dimensional stuff, it works. Alright,
My
yeah.
family watches that.
In the table below, draw an example.
Guys, we need to math. Have you seen
Draw an example
No joke.
of a graph that represents the different solving outcomes of a system of linear
There's
equations.
like a million-yard field flipper gas.
So let's draw, actually, let's do this. You guys try to draw any system that has only one solution. And that looks really good, actually. Right? So if I do these, I just want one solution, right? Bam,
Just draw an X.
there's a nice line. And let's draw another in something like these. Bam. Now we don't have to identify what the actual answer is, but we can see that these 2 lines intersect once, right here. What about one that has no solution?
Two parallel lines.
That sounds great. We just need parallel lines.
Tragic love story.
So I got something like these.
Wait, could it be?
Oh, whoops, that's not supposed to
Could
happen.
it be a parallel line that goes straight up?
Let's try something like these. I mean, if you really wanted to, you could draw another line. Because drawing lines is so fun. Bam.
Best we're all stuck in a forever.
All right, let's draw one that has infinite solutions. Done. There it is. All right, so now we should be able to determine if 2 equations have one infinite or no solutions. And on these, really all we need to do first is look at the sloppage right here. Well, these sloppages are different, therefore, one solution. Right here. Now, this.
Wait, how would you check your?
Neither of these are in slope-intercept form, okay? To check the work, we're just looking for the sloppages. Now, in this one,
Like, would you have to check your work on this thing?
no, not really. We got to subtract the, yeah?
Oh, never mind.
Yeah, subtract 2/3 x, right? So minus 2/3 x. So this one ends up being y equals negative 2/3 x plus a 1. Well, now we got this sloppage, which is the same as this sloppage, but the y-intercepts are different. So this one has no solution.
Ah, the tragedy.
It is, right? Like this one, in fact, will be very similar to what you were saying, because when we subtract 2x from both sides, right here, we get y equals negative 2x plus 8. Well, right here, right off the bat, we see that these 2 sloppages, they may look the same, but they're definitely different. Therefore, we have only one solution.
Wait, is A actually just one solution?
All right, what do you guys think about D?
Infinite.
We could change these into slope-intercept form, right? By subtracting an x from both sides. So this one is y equals negative x and then a plus 5. And over here, we would have to add 2x. So that's a negative 2y equals 2x, and then we have that negative 10. Just divide by negative 2 everywhere. And we get y equals negative x plus a 5. Well, these two equations are written exactly the same.
So they are.
Therefore, this one has infinite solution.
It's not the tragedy, it's the best one.
Yes, this is a best case
No
scenario.
conflicts whatsoever.
It's the Disney ending.
Towards the end, there would be just like this little like bump. when
No,
you-
that's like work their way up to like being
But we just skipped
Disney
three
princess.
different
Trying to be
I like these
I mean,
types
you
of
can't just
movies as long as
start
there's
out
like
being
explosions
princess,
and
like,
and violence.
Like,
It's like a,
Movies where the main character's parents know.
it's an action-packed romantic comedy. The Princess Bride. I nailed it. All right, what's the answer for E?
Name one Disney
No
movie
movie
where
will
both you see both of the main characters' parents.
Let's find out.
No selection.
Here we go.
That's what I.
Let's subtract 3x from both sides. Oh, what the heck?
Subtraction.
Minus 3x, so we got 2y equals negative 3x plus a 5er. Then we'll divide everywhere by 2. So y equals negative 3 halves x plus a 5 half. Now over here we'll do the same thing, minus 3x from both sides. 2y equals negative 3x plus a 6. Divide everywhere by 2. And we got y equals negative 3 halves x plus 3. 3 is pretty close to 5 halves, but it's not the same. Therefore, this one
It's
has
a real tragedy.
no
Like, a
solution.
half-
Wait, so how do you figure out whether or not it has no solutions or like,
It's a great question. This one has no solutions because
or how do you figure
having
out
the
that-
same sloppage makes them parallel. The y-intercepts being different is what makes them never ever meet.
So how do you know if they do?
All right, what about these?
Hey, well, oh,
What's the answer for these?
the last one or the numbered one?
This is number F.
Oh, it's infinite.
Is it solution or solutions?
Solution.
Solutions, how many? 0 or infinite?
Infinite.
Infinite. These end up being the same equations. Which would be this one?
Right, a second.
All right, on a test. On the test, you can expect problems like these three, where you have to make up your own equation, which has one solution with this one, no solutions, and infinite solutions. So since that's the case, what I would recommend doing is changing this into slope-intercept form. All right, so we'll subtract 6x from both sides. I'm going to switch these around. I got 4y equals negative 6x minus 12. And then divide everywhere by 4. So I got y equals negative 3 halves x minus 3. So that's the equation I have. What would be an equation that has one solution? Y equals
3 halves minus 3.
As long as the sloppage is not negative 3 halves, we're good. So we can just say x. I don't want to write too much because I'm old.
Y equals x minus 3.
Y equals x minus 3 would work. Y equals 5x, negative 5x, plus 3, whatever. Any of those things, okay? What about one that has no solutions?
So y equals x would work.
Yeah, because the sloppages are different.
Oh.
This one, y equals, yeah?
Negative 1 or 1.5.
Negative,
3 halves, I mean.
that's good.
Plus 5.
X plus a 5er, bam. This one would be infinite, I'm sorry, no solutions. Thank you, because Sloppage is the same, y-intercept is different. What about one that has infinite solutions?
An exact copy of it.
Yeah, just copy it down. Y equals negative 3 halves x minus 3.
Oh, what these two equations that will make go right.
All right, there's the full page if you guys wanted to stare at that garbage. One method for solving simultaneous linear equations is graphing. In this method, both equations are graphed on the same coordinate grid and the solution is found at the point where the two lines intersect. So, one of these is actually kind of hard to graph, well, if we just left it as it is. But we can manipulate it so that it would become a little bit easier to graph. So what type of problems would we expect to encounter graphing at these? Well, specifically for the top equation, we may have to manipulate the equation into slope-intercept form. Because that top equation right there is definitely not in slope-intercept form. That is in standard form, which is no good. But slope-intercept form is good because it gives us a y-intercept. That gives us a point to start with, and then we use the sloppage to figure out where all the other points are. What form of linear equations do we typically use when graphing? Well, generally, we use a slope-intercept form, which, if we didn't know it already, is y equals mx plus a b. As we have seen, it is possible to rearrange the equation that is not in slope-intercept form using the same rules we solved equations with. We can rearrange this equation to put it in slope-intercept form. Remember, it's y equals mx plus b, so the idea is to get y by itself on the left side of the equation, and we'll rearrange the right side so that we have the sloppage first with the x and the y-intercept thereafter. Alright, so if we actually show the work on these, what we would do is subtract 2x from both sides, and then we get this next equation, and then all we've got to do is separate these two terms, 4 and negative 2x, and then we're just going to switch these around to get this slope-intercept form. So this is only useful because sometimes they will give you guys these equations in not slope-intercept form. And we just got to manipulate it until it is in slope-intercept form. Alright, let's look at an example right here, and apparently with your teacher's help, write in the steps you complete as you go. So the first thing we would do right here is to subtract 4x from both sides. And now we'll show the work for these. So let's go ahead and subtract 4x from both sides. And then we get this next equation. At this point, it looks like they divided everywhere by the coefficient of y, which was negative 8. And so now we'll specify that. Divide all terms by the coefficient. I just broke my desk. Thank you. Of y. That's still a lot.
No, it's not.
Now that we have these, all we're going to do is rearrange these two terms so that the positive 1/2 x is in the front and the negative 2 is not. Bam. Rearrange into y equals mx plus a b, not mix. There we go. And that's it. Then we are done. Put the following equations in the slope-intercept form. There we go. So this one right here, we got the 5x on the same side of the equal sign as the y, so we will subtract 5x from both sides. So this gives us a y equals 9 minus a 5x, and, well, all we need to do now is to switch these two. So we got a y equals a negative 5x, and then a positive 9er. That would be all. Alright, B. Same idea on at these. We got the 4x being added to the 2y. If we could make it a 0, then all the better. Okay. So this does become a 0 right here by subtracting 4x. And then we got the 2y equals negative 12 minus 4x. Well, we don't want that 2 in front of the y, so we can divide everywhere by 2. And we get y now equals negative 6 minus 2x. But this really isn't still in formal slope-intercept form. So we'll just move those around and make this y equals negative 2x minus a 6. Alright, we get kind of used to just moving that first term over to the other side. So be careful not to subtract 4y from both sides. Let's just go ahead and add x to both sides, like these. Giving us a 0 right here. Still got this 4y, but now it equals 16 plus x. Now I'm going to switch these right now, so we'll make this x plus 16. And it doesn't matter which order you do it in. 4y equals these. The x, I'm going to put the coefficient there. It was just a phantom one, so we couldn't see it. I'm going to make it not a phantom one, so we can see it. And from right here, we would divide all the terms by the coefficient of y, which is 4. Well, those 4's become a 1, so we got y equals, I'm going to make this 1/4 x plus 16 divided by 4 is 4. There it is. So again, the same idea. Let us go ahead and subtract 4x from both sides. So now we got negative 2y equals negative 24 minus a 4x. So again, I'm going to switch these two, giving us negative 4x minus 24 equals negative a 2y. So to solve, we'll just divide all the terms by the coefficient of y, which is negative 2. And we get a y equals 2x plus 12. Bam. So that's a lot of them right there, but you have to be able to graph these as well in order to really do the homework tonight. So in addition to being able to change these into slope-intercept form, you need to be able to graph them. Alright, problems like this one really aren't too bad. Here's what we got. The coefficient of y is actually negative 1. Make that a 1 right there. So we don't want a negative y though, we want a positive y. So to do that, we'll just divide all the terms by negative 1. So again, that becomes a positive 1. We got a y equals x divided by negative 1 is negative x or negative 1x, doesn't matter. Negative 2 divided by negative 1 is a positive 2. There we go. And of course, if you didn't show the coefficient or change that 1 to a phantom one, that's okay. So right here, I will skip that step. Let's show it though. We need to add 2x to both sides to get the y's on their own side. So again, that step may be skipped and we can show that we're going to switch the 2x and the 3 right now. But then we've got to divide everywhere by 5. And this 5 has become 1. That's good. Then we got y equals 2/5 of an x plus 3/5. That's it. Well, that was that whole page. So these are the equations that we had. Of course, we already changed this equation right here into slope-intercept form, which was a y equals negative 2x plus a 4. And then we got the other equation, y equals 4x minus 2. So it wants us to graph these two equations, which we will do. Now I'm going to do these in different colors so we can tell the difference of which one is which. The red one will be y equals negative 2x plus 4. So that gives us a y-intercept of 0, 4 and a sloppage of negative 2 over 1. So from 0, 4, which is right here, the y-intercept, we're going to go down 2 and to the right one, and down 2 to the right one. And each of these stair steps is showing us where each next point is. And I can continue the pattern to the left as well. So I should have these points as well. Now I can draw the line that goes through these like these. So that's that equation. And we use the stair steps, which is great. Now I'm going to do y equals 4x minus 2. So this y-intercept at 0, negative 2. And a sloppage of 4 over 1. So from right here, I'd go up 4 to the right one, up 4, wait, 1, 2, 3, 4. That's better. There's my next point, up 4 to the right one, there's my next point. Of course I can continue this way as well, and that would be okay. Well, now I'm ready to draw the line through these purple points. And there's my line. So now instead of drawing one line, we're drawing two. But the real question on these is where on this graph do the two lines intersect? Well, it looks like it's this point right here, which has a value of 1, 2. As it turns out, this is the answer to a system of equations. It's where the two lines intersect on the graph. It's an x value and a y value. So that takes us to what a system of equations is, where we have more than one equation, and we want to find out where the two equations are equal. It's kind of like comparing the price of two different, places. Like saying, hey, how much does it cost to have a party at Bozo the Clown's versus Zazie the Clown? And wherever they're equal would be this point. You could bring one person and it costs $2. Bam. All right. Now, well, you can enjoy it. All right. Let me rephrase that. I can enjoy giving it to you. All right. So we got these two equations. We got 2x plus a y equals 4. And then we got a y equals 4x minus 2. So part B, it tells us to verify this garbage. And we can see right down here that the x value is 1 and the y value is 2, right? That's an ordered pair. So I'm going to go up here and I'm going to replace the x's and the y's with their respective values. X is 1, y is 2. And I need to verify to make sure that this would be a true statement. If it's false, then this point that we think is the answer is not actually the answer. So 2 times 1 is 2, plus 2, this should equal 4. 2 plus 2 is 4. 4 does equal 4, that's true. So I know it works for that equation. Next, I need to use it in the other equation, so I'm replacing y and x. And down here we see that y is 2 and x is 1. So solving at these, 4 times 1 is 4, minus 2 should equal 2. 2 equals 4 minus 2 is 2. That's true. Since it's true, we've just verified that the answer is correct. The problem is that it's checking our work. And unfortunately, only about one person per class will actually check their work, even if it's a short, small test. Okay? So a calculator could verify this for you as well if you just punched it in there. But again, with all that extra work, usually only about one person will do it.
Yeah, true.
But do it, because it's a good way to guarantee that you get 100%
Yeah, but then
on a
it
test.
takes you forever.
If by chance you found that one of these gave you a false statement, you'd have to go back and see where you made a mistake. If you don't, then you're just putting on the test and a wrong answer, and you know it's wrong, but you're not going to do anything about it. So don't just leave it. The solution, or solutions, to a pair of simultaneous linear equations is all pairs, if any, of numbers x, y that are solutions for both equations. That means that x, y satisfies both equations, like after you eat a Snickers bar. When solved graphically, the solution is the point or points of intersection, if there is one. So 6 and 7, that we will be doing, would be like checking to see if our answer is correct, just like we did on that last problem. But it's important for you guys to realize that that ordered pair is where the two lines intersect. So if we graph it, we can find out where the two lines intersect. Bam, we have our answer. Determine whether 3, 8 is a solution to the following system of equations. Alright, so I got 2x plus y equals 14. My x value is 3. Y value is 8. Again, I need to make sure this is true. So I'm going to replace x with 3 and y with 8. Bam, 3 and 8. I just want to make sure this is true. 2 times 3 is 6, plus 8. This needs to equal 14. In my calculator, because this is really hard, 6 plus 8 is 14. And 14 does equal 14 is true. But that's not all. We got to do it to the other equation. X plus y equals 11. But again, I'm going to replace x and a y with 3 and 8. 3 plus 8 is 11. Does equal 11. That's true. So this one is a solution. Alright, what about 7? Now again, this is what you do after you find your answer, to make sure that your answer is correct. Okay? So I'm going to go back to my equation. Y equals 2x minus a 5. And I'll replace a y and x with their respective values, 0 and negative 5. So 2 times 0, and this should equal negative 5 right here. 2 times 0 is 0 minus 5. Should equal negative 5. Negative 5 does equal negative 5, so this is true. But again, we need to check that other equation. 4x plus a 5 of y equals a 25. So I'll replace x and y. X is 0. Y is negative 5. 4 times 0 is 0, plus 5 times negative 5 is negative 25.
Equals 25.
That's a negative 25.
Yeah.
Equals 25.
Incorrect.
0 minus 25 is negative 25,
So it's incorrect.
which equals 25, which is false.
False.
Since that is false, it's not a solution.
Solution.
Therefore, you'd have to go back and figure out what the heck you did wrong.
Yeah.
Right there, okay? Consider these two equations. This is the next page, by the way. Make sure both equations are written in slope-intercept form, which these two are. Then we will graph them on the graph, or grid, and then we'll find the solution, and then we can verify. Alright, well, we got both these equations. This red one, y equals negative 2x, we can make that plus 0 if we really want to, but whether we do or not doesn't matter. The y-intercept is still 0, 0. And then we got a sloppage of negative 2. I'm going to make that negative 2 over 1. So you can put the stair steps in there. But we'll make this one look a little bit more clean. And these are our points, which now I will connect using a line.
Like line.
Bam, there it is. Alright, so that is that line. Now we need the purple one, which has a y-intercept of 0, -3, and a sloppage of, I'm going to make that down 1 to the right 2. So 0, -3 right here, down 1 to the right 2, and that pattern continues. But it also continues to the left. There it is. Now I'll connect these with a line like these. And we can see right now where the point of intersection be. Right here. Yeah, that's very good. That's at the point 2, -4. But then it wanted us to verify this garbage, so let's do that. Alright, so I got y equals -2x and y equals -1/2x minus 3. And the point that I found we'll replace with the x and y values in both of the d's. And the x value was 2. And the y value was -4. So solving at these, -2 times 2 is -4. This one is true. What about the next one? -1/2 times 2 is -1 minus 3 should equal -4. Well, then we got -1 minus 3, which is -4, which does equal -4. That's true as well. Therefore, we know that this answer is correct. This is the beauty about lines. Oh, there is. This is the beautiful thing about them, is that, see how they kind of come together right there, right?
Like you
And it's kind of like one of those Shakespearean plays.
united,
They meet once,
they died.
and then they drift apart forever and ever and ever. Well, what about this next one?
Nixon.
We got -2x.
Is that a what?
Oh, sure.
Nixon.
Let's look at this one. Let's change this into slope-intercept form. So we got -2x plus a y equals -1. And we'll change this one into slope-intercept form. We'll add 2x to both sides. What's that?
Did you know it's Friday?
Oh yeah, there we go. That's
Did you
better.
know it's
Thank you.
Friday?
Well, this becomes a y equals a 2x minus a 1. And then the other equation that we had, y equals 2x plus 4. And we'll graph that one in purple. Alright, so my y-intercept for the purple one is 0, 4, with the sloppage of 2. I'll make that 2 over 1. So 0, 4 is right here. And then I'll go up 2 to the right one and continue that pattern. And then I can go backwards as well.
Backwards.
A little backwards. Alright, then I'll connect these points with the line. That's very nice. Now let's graph the red one. And we have a y-intercept at 0, -1 with a sloppage of 2 over 1. So 0, -1 right here. And then we got our points up 2 to the right one continually. And then down 2 to the left one. Like these. So let's graph this one. And yes, these two are parallel. So the real question is, when do they meet? They never do. So this one actually has no solution.
So this is the story of when Ariel and
No, this one's one of those highly dramatic ones that make you cry at the end. Right? The two lines, they have so much in common, but they never meet. Which is kind of sad. All right, now it's your guys' turn on the back side here. Draw two lines that have only one solution.
I got you.
Lines that you guys draw will probably be different than the ones that I draw. All right, here I go. You guys done? Yeah. One more time.
I dropped off, I drew lines.
Bam, there it is.
But you didn't draw the line.
That's one of them. I need to draw another one, right? Bam.
Infinite many solutions.
That is not one solution.
Oh.
Nailed it.
I did a good one.
I got it. And we can see that the solution to these would be radical.
I did.
Yeah, here's.
All right, now draw two lines that have no solution. All right, here we go. Let's draw these. So I can have a line, let's say I got this a line radical. That looks pretty good. And then my other line can be radical. There we go. Maybe some people want to draw three lines for some reason. I don't know.
I did it.
You just never know, okay? That would work. All right. So these ones would have no solutions because they're parallel. They never meet.
Yeah.
Now draw two lines that have infinite solutions.
I did that one.
Bam, let's do it. All right. So I got this line radical. And then the next line would be this line radical. Bam, I nailed it. These two lines have infinite solutions because they meet everywhere. So we have to determine the difference. Yeah, both of you, gosh. So here's the thing you guys need to remember on it, these. The one solution problems, they will have the different sloppages. The no solutions will have same sloppage, but different y-intercepts.
Are we all done?
And then infinite solutions will just be, it just usually ends up being the same equation. Bam. You guys have to determine for these if they have one solution, no solution, or infinite solutions. So with these, here's my sloppage 8. This is a sloppage of -4.
No.
These ones have different sloppages, one solution.
Wait, how do you know if this one?
B. Well, what's the answer to a D's?
Locked.
All right. This one, after we change this equation in the slope-intercept form, has the same sloppage but different y-intercepts. No solution.
Look at that.
Now the D, if we change these to slope-intercept form, put on my desk, please. Then we would find that these have the same equations. Just make this infinite solution. All right. No. Never. Not in this class. It's math. Here we go. C. One, none, or all.
Oh, none. Oh,
Excellent. This one has
none.
one.
One.
What? I knew it.
I knew that.
Solutions.
No.
Yeah. 2 divided by 2 is 1.
Wait, I'm a little bit confused. Wait.
No, this one is not yet in slope-intercept form. So by changing it, we get y equals -2x plus 8.
Wait, I have a question.
These are differing sloppages, therefore it's one solutions.
Wait, is the
All right, E. One, none, or infinite? Yeah, no solutions on it, these.
Says none.
One, none, or infinite?
infinite? No.
One.
This one has. Oh,
One. Two. None.
0?
I got it. That's what I said. I said no.
What? Wait, what?
Why?
It's the same.
Yeah.
So it's
No.
infinite.
That's what I put.
You said no. You got me really.
Oh, sorry, no. I usually do the one circle and then the other one. My bad. It was just a little out of order.
But you confused.
All right, now it's your turn. You guys need to write an equation compared to this one that would give you one solutions, no solutions, and infinite solutions. All right, here we go. So the first thing I'm going to do is change this equation in the slope-intercept form by subtracting 6x from both sides. And now we got 4y equals negative 6x minus 12. And then we'll divide everywhere by 4, which leaves us with y equals negative 3/2 x minus 3. Well, this gives us a sloppage of negative 3/2 and the y-intercept of 0, negative 3. So when we write an equation that has one solution, we just need the sloppage to be different. Y equals x would work. Y equals 3x would work. 3/2 would even work. We just can't make that negative is all. And whatever you plus or minus, whether it's 0, 10, 105, 1.05, all of those work.
Why can't we make it negative?
All right, now B, this will be a different equation. But again, we're comparing it to our original equation, 6x plus 4y equals negative 12. But we changed it in the slope-intercept form. So we just need another equation that would give us no solutions with that one. So we got y equals mx. So on this one, we need the same sloppage, which is negative 3/2. But we need a different y-intercept, like, I don't know, 0.
Yeah.
Maybe 30.
Yeah.
Maybe negative 30.
Yeah.
Maybe 730. Who knows? Okay? It doesn't matter what that y-intercept is, as long as it is not negative 3. Next up is infinite many solutions, which is y equals, this one we want the same sloppage, negative 3/2 x. And we want the same y-intercept, which is negative 3. Bam. There they are, all three of them.
That's how you do it.
Alright, well there's the whole page if you guys like it. Well, even if you don't like it.